A prediction without an error bar is just an opinion. In fusion, opinions are cheap and consequences are not. So the most important thing a Kronos model produces is not a number. It is a number with an honest measure of how much to trust it. Every forecast the twin makes comes with uncertainty attached. Not a single value for the plasma state, but a value plus a range. A band that says, given what I know, the truth most likely lives in here. That band is not decoration. It is what tells the control system when to lean on a prediction and when to hold back. Uncertainty comes in two kinds, and separating them matters. The first is aleatoric, the irreducible noise in the world itself, the randomness you cannot train away. The second is epistemic, the model's own ignorance, the gaps where it simply has not seen enough data. You reduce epistemic uncertainty by learning more. You can only respect the aleatoric kind. Then comes the hardest question. Are the error bars honest? A model can be confident and wrong. So we check calibration. When the model says it is 90% sure, is it actually right 90% of the time? We plot that. Predicted confidence against real outcomes. And a well-calibrated system sits on the diagonal. If it drifts off, the uncertainty is lying, and we fix it. To build those bands in the first place, we don't trust a single run. We use ensembles and Monte Carlo sampling. Many models, many draws, each with slightly different assumptions, and let the spread of their answers become the distribution. Agreement means confidence. Disagreement is the model telling you, honestly, that it does not know. We also ask which inputs actually matter. Sensitivity analysis traces the output back to its drivers. Which measurement, which parameter, moves the result most? That tells us where to put our best sensors, where the physics is fragile, and where a small error propagates into a big one. All of this feeds one loop we take very seriously: verification and validation. Verification asks, are we solving the equations right? Validation asks, are we solving the right equations? Does the model match reality? Every claim we make is benchmarked against known results and ultimately against experiment. That is the credibility loop, and it never closes for good, which is why we label our claims plainly. Shown means demonstrated in simulation or data. Gate means a real physics or engineering hurdle we have not cleared yet. Assumed means an input we have taken as given. When a viewer sees a Kronos result, they can see exactly which of the three it is. No blurring the demonstrated into the hoped for. Now, reproducibility. A result you cannot reproduce is not a result. We hold two tiers. Tier 1 is byte exact. The same seeds, the same containers, the same code, producing the identical output down to the last bit. Tier 2 is tolerance exact. Run it on different hardware and land within a stated numerical tolerance. Both together mean the science stands on its own, independent of the machine it ran on. That demands discipline underneath, fixed random seeds, containerized environments, and full provenance. Every result traceable back to the exact code and data that made it. No result floating free of its recipe. And then we publish it. Code, data, methods, open. The breeder, the burner, and the AI and quantum work each carry a permanent public DOI, so anyone can pull the record and check our arithmetic. Open science is not a marketing posture here. It is the mechanism that makes the uncertainty honest. Because in the end, credibility is the product. Fusion has never lacked bold claims. What it has lacked is claims you can audit, error bars you can trust, validation you can inspect, results you can reproduce. That is the foundation everything else